Let's have a brief introduction to isomorphism and equivalence relations. Okay, so let's talk about isomorphism first. What is isomorphism? Actually, isomorphism is a feature or a characteristic to a linear mapping. Let's suppose we have a linear map T such that B to W. Now, this mapping is said to be isomorphism if and only if it is injective as well as surjective. It's injective as well as surjective. So we can say that a bijective mapping, it's called a bijective linear mapping, is called isomorphism. If you see, or if you consider the previous case, a mapping of vector to its coordinate vector, then that is actually isomorphism, since we have already seen that it was injective as well as surjective. So we can say that a mapping which goes from a vector to its corresponding coordinate vector, that mapping is isomorphism, since it is both injective as well as surjective. This is just a brief introduction or the definition of the injective vector. Sorry, not the injective vector, but the isomorphism. Now let's talk about equivalence relations. Let's talk about equivalence relation. Now, equivalence relation. So before understanding equivalence relation, we have to understand the components of the equivalence relation, the reflexive, symmetric, and transitive uh, relations. Okay, so now let's see this. So let's suppose we have X, which is a non-empty set, and let's suppose X belongs to the non-empty set X. If that's the case, then a mapping exists such that X maps to X for all X belongs to X, and such relation is called reflexive relation. Okay. Similarly, if we suppose that there exists a mapping such that X maps to Y and Y maps to X for all X and Y belongs to X, then this is called the symmetric relation. Similarly, if we consider there exists a mapping such that X maps to Y, Y maps to Z, and then X maps to Z for all X, Y, Z belongs to X, then such relation is called transitive relation. So what does that mean? It means that there are different kind of relations. Okay, if we consider a non-empty set and we consider a lot of vectors, let's suppose X, Y, Z are, or we can say X, Y, Z exist in that non-empty set, and if that is the case, then a lot of relations are possible, and among them, this particular type of mapping or the relation where each, or we can say where one of the vectors inside the non-empty set maps to itself, then that is said to be the reflexive relation, and similarly the other ones. So these are just the definitions of what are the different kind of relations that may exist. If we consider that we have a non-empty set X and we have a non-empty set X, and in which all of these three properties or all of these three relations exist, then that is said to be the equivalent or equivalence relation on X. Okay, then that is said to be an equivalence relation on X. So that means equivalence relation on X means the relation must be reflexive, transitive, as well as symmetric. This is the relation, or sorry, this is the definition of the equivalence relation. Now let's try to understand the relationship between isomorphism that we previously discussed and the equivalence equivalence relation that we just discussed. Okay. Now it turns out that the relation of isomorphism between two vector spaces is an equivalence relation. That means if we consider two vector spaces, let's suppose V and W, and if we consider that we have isomorphism, okay, wait a second. It says that the relation of isomorphism between two vector spaces is an equivalence relation. Okay, and we know that for a linear map to be isomorphism, it must be injective and surjective. That means if we consider two vector spaces, let's suppose our vector spaces are V and W, and the mapping in between them is injective as well as surjective, then this mapping has three relations. What are they? They are reflexive, symmetric, and transitive relations. Now let's see this and let's try to prove this theorem. Okay, let's try to understand this theorem. It says that the relation of isomorphism between two vector spaces is an equivalence relation. Now to provide the proof of it, we need to first consider some of the things. And the first consideration is that this wiggle here, this wiggle sign, is considered to be the relation of isomorphism between the two vector spaces V and W. If we consider that, then we have to show that since V and W are isomorphic, we have to show that this isomorphic means that V and W are also equivalents. And equivalence means we need to consider three of the property: reflexive, transitive, and symmetric. So let's see. Now our first initial guess is that this is isomorphic. So we have to show that the equivalence relations. So for the equivalence relation, the first one is reflexive, and to show that this isomorphic relation is also a reflexive relation, we considered an identity mapping of V to V. Now, since V is mapping to V itself, then it is injective as well as surjective by definition. That's why we don't have to talk much about its isomorphism characteristic. But for the reflexive characteristic, we can say that since it is mapping to itself, that means if we consider any vectors x or y which lies in this non-empty vector, non-empty set, then that also be the case that this x must map with x and y must map with y. That is the reflexive relation. So it is proved. Okay, it is proved that if it's isomorphic, this identity map exists, then isomorphism as well as reflexive relation exist. Now let's see for the other cases, for the symmetric and the transitive relations. Again here we have considered the similar cases. First we consider the isomorphism between V and W, and if these are isomorphism, that means there exists a transformation between two vector spaces V and W, which looks like this. Now we also know from the properties of the transformation that if we consider the inverse of the transformation, then the range set becomes the domain set and the domain set becomes the range set. That means if this type of transformation exists, then this type of transformation, which is inverse transformation of T inverse such that W maps to V, must also exist. And we can consider that this looks like the inverse of it, or we can say that these two transformations are symmetric. That's why it shows that if we if our initial guess was this, then since this also exists, then this relation must exist. these two relations is called symmetric. So this is also proven. Now the third relation is transitive relation. Now to be transitive relation, our initial guess exists as it is, and we also add our another guess, which is W is also isomorphic to U. If that is the case, then there exist two transformations, two linear transformations, such that T maps to V, T such that V maps to W, and S such that W maps to U. If these two mapping exist, then we can consider, or we can integrate these two mapping into a single one, and we can say that the mapping or the linear mapping from V to U must also exist. That means a relation or an isomorphic relation V U must exist, right? And now this is the transitive relation, because we have already, our initial guesses was this and this exist, and from these two we have concluded that this also or this must exist. So that means this is a transitive relation. So in this way, our isomorphic relation must be an equivalence relation theorem is proved. Let's see this theorem, which says that if a vector space has a finite basis, then all of its bases have the same number of elements. What does it mean? It means that if we consider two bases or maybe three bases, no matter what, a lot of bases. So if we consider a lot of bases, then to consider that these that to okay, so we can say to verify your claim, these are the bases of the vector space V. One of the criteria need to be fulfilled, and that is that all the dimensions of all these bases must be equal. And why is it true? Because of this proof. Let's see. Let's suppose we consider not the uh, infinite number of bases, but let's, for the simplicity, let's take two bases. B and C be the two bases, and B is composed of ui's, where I goes from 1 to n, and C is made up of vi's, where I goes from 1 to n. So if these two are the bases, then we can consider that if, now let's see, since C is a basis, that means it must be the linear combination of something, right? So let's suppose that the element that lies in this basis actually form the linear combination of this, which is true from the perspective of the definition of basis. So let's suppose that, let's suppose that u1, which is a component of this basis, be a linear combination of these basis vectors. Okay, if we consider that, then we get u1, u2 up to un, and these are the linear combinations that we get. Now since B is also a basis, so we can consider that since B is also a basis, so it must be a linear combination in U. Now we have defined ui's to be these linear combinations, so we can substitute u1 with the linear combination of u with respect to v, which is this, plus b2 and the linear combination with respect to vi's, again in a similar way. And now what we can do is we can construct a linear combination only for the v1, similarly only for the v2, and similarly up to only for the vn. Okay, now this would be the linear combination. Now as we have already seen from the definition of the basis that these coefficients that we use for making the linear combination must be linearly independent. That means if we consider this whole system to be zero, then these bases are not 0, but all of these constants, coefficient constant must be 0. If we consider that, then it turns out that the m and n, we have considered the bases, the number of bases to be n. Okay, I didn't tell you earlier that. So see, we have considered that B has n number of bases and C has m number of bases, and where m is not equals to n. That means we have considered that the number of the bases is different, and after equating these to 0, you come to the conclusion that it won't work. It won't work if n is not equals to n. It has to be the case that m must be equal to n. Okay, for the linear combination of this to be consistent. So that is it. Now let's talk about another topic, which is finite dimensional and infinite dimensional vector spaces. Let's see the definition of finite dimensional and infinite dimensional vector spaces. If a vector space has a basis which has finite number of basis vectors, then that vector space is said to be finite dimensional vector space. And if the basis vector are of the infinite number, then that is said to be the vector space. That is said to be the infinite vector space. It means that the term dimension depend upon the number of basis vectors. If we have a vector space and the bases of the vector space are infinitely large, then that vector space is said to be infinite vector space. But we have definite number of vectors are the basis vectors, then we can say that that vector space is a finite vector space. Okay, there is not much to talk about it. Now let's go to our theorem. Okay, let's see this theorem. It says that two finite dimensional vector spaces are isomorphic to each other if and only if their dimensions are same. So for the proof of it, we considered two vector spaces u and v, which has the basis this and this respectively for both u and v. Then we considered a linear mapping where T is such that u maps to v is an equivalence relation. Okay, so what we did is we considered a linear mapping between u and v, and we considered that this linear mapping is equivalence relation between u and v. If that is the case, then it means that u maps to u and v maps to v. That means it's a reflexive relation. And if u maps to v, then v maps to u. That means it's a symmetric relation. And if we consider w to be any other vector space with the same dimension or the same number of dimensions, then u maps to v, v maps to u, implies that u also maps to w from the transitive relation. Now since this mapping T such that u maps to w is an equivalence relation, then from the previous theorem we can say that since it's an equivalence relation between u and v, it must be an isomorphic relation too. Okay, so this is how we didn't do it by the lengthy process, but by using our shortcut and by using our previous theorem on relation between isomorphism and equivalence relation, we proved it in a very clever way. Okay, now let's see other theorems associated with uh, finite and infinite dimensional vector spaces. Here we have a relatively easy theorem, which says that the span of a set is not affected by removing from the set one element that is a linear combination of other remaining elements of that set. For proving it, we consider that a vector space V has a basis Vi, where I goes from 1 to n, and then we consider that X belongs to V such that X is a linear combination of all of these basis vectors And let's suppose we have a linear combination of any vector, any basis vector. If we consider that V1 is a linear combination of V2, then what we do is we substitute V1 with its linear combination. If we do that, then we find out that this can be written in this form such that we get a linear combination, another linear combination excluding V1 but including all the other vectors. Okay, so that means that here we again got a linear combination X, and it proves the theorem that the span of a set is not affected by removing the removing from the set one element that is a linear combination of other remaining elements of the set. Okay. Okay, so this is a very simple theorem, but you have to listen to the words, okay, very carefully to really get it. So the theorem says if a set of n vectors spans a n-dimensional vector space, then set is a basis for the vector space. So what are the key words here? The key words here are, first one is basis and second one is a span. So let's suppose V is a vector space, and now okay, yes, let's V be the vector space and let the set of n vectors be these. Then if we consider the linear combination of the set of vector of these vectors, then it will form a linear combination which looks like this. Now for U to lie in vector space V, the set of these vectors must be basis, and for the basis these vectors here must form a linear combination, but an independent linear combination. So they always have to form an independent linear combination. Okay, so we have to show that these set of vectors always form a linear, actually, yes, linearly independent combination. But let's prove it by using uh, proof by contradiction, and let's suppose that it doesn't form a linearly independent combination. If we consider that, then some of the vectors of this may be the linear combinations of others. But by the previous theorem, uh, have already known that removing some of the vectors from these combinations, from the linear combination, does not necessarily changes the span. Okay, that means even if we remove uh, some vectors vectors from the vectors set of vectors, the remaining vectors would span and form a linearly independent set. And since they are linearly independent, so we can consider them to be the basis. And since they are basis, so we can say that these set form the basis for any vector space V. So I think you understand it.